All right, watch this.
Imagine, if you will, a state dinner at the White House. These are not small, intimate affairs. 300 or so adults mingle in close quarters, yet somehow it's a quiet gathering where people behave gently, move around slowly, and almost never run into a wall. However, as a group, they do take up a lot of space, they give off a lot of heat, and lots of things get moved around. In these ways, the room is changed by their very presence. Now picture a 5-year-old's birthday party. Very different situation. You would not call that quiet or formal. But that is not enough. Imagine the most popular 5-year-old in the world, his birthday party. 300 kindergartners in one room for several hours, shoving each other, running like crazy, and definitely banging into walls. Their bodies are smaller, but because of their faster motion, they collectively take up just as much of the room and give off just as much heat as the slow-moving adults do. And things get shoved around just as much. Now imagine we have a surprise for those 300 adults at the state dinner, all very formal and tucked in. There are 300 5-year-olds in the next room, bouncing off the walls, and suddenly we drop the wall. Excellent. First of all, those kids are going to run all around the room, squeezing in between the more sedate adults. That will cause the adults to move apart a little, maybe even bumping into a wall now and again. But because the adults are moving more slowly, they'll get in the way of the kids running and slow them down some. That might even cause the kids to run to the walls a little less often. The most important thing here is that the overall bouncing against walls will be equal to the bouncing of the adults plus the bouncing of the kids when they were in separate rooms. And you will not be shocked to find that we are currently in amongst an elaborate analogy to do with gases.
Okay, so believe it or not, in the real world, those little kids are not going to be able to get into the state dinner with the president. It's just not going to happen. And if it does, then weird things will happen. But if gas A were adults and gas B were little kids, and you were to mix them together, they mix. Not only that, they would mix in a predictable way. Because in the world of gas laws, we don't care how big you are, we don't care how important you are, we don't care how old you are. All we care about is how many of you there are. Okay? And that is Dalton's Law. For example, if you're going to go do some deep sea fishing, deep sea scuba diving, what kind of air would you use? You would use helium plus oxygen. Okay, that's going to be a whole lot more expensive than just bottling air, which is nitrogen plus oxygen. Does anyone know why you would need to use helium plus oxygen instead of nitrogen plus oxygen? Yes. Okay, what does that have to do with the pressure? Nitrogen is in the air that we breathe. We take a deep breath, and the nitrogen simply at this pressure cannot get into our blood. The oxygen can, but not the nitrogen. Even if it did, nitrogen wouldn't do anything. It would just stay as a teeny tiny little bubble in our bloodstream. Okay? So nitrogen at our pressure, not going to bother. But let's say we put all that nitrogen, oxygen, air in a scuba tank and you go down, down. You know that in a 6-foot pool, you go down, you can feel the pressure. Can you imagine going down 20, 30, 50 feet? At those pressures, the nitrogen is absorbed into your bloodstream along with the oxygen. Which, no biggie. It'll come back out as you slowly arise. And that's the key. You must always remember that however long you took to go down there, that's how long you should take to go back. So if you have 2 hours worth of air, time yourself. Because once you get a little bit below half, you need to start back. Why? Because those nitrogen bubbles. Let's say you are minding your own business in a beautiful coral reef, just enjoying it, and you go face to face, you come face to face with a hungry shark. You're going to want to get away from the hungry shark because you don't want to become a hungry shark meal. So you're going to look up, oh, there's a surface 60 feet up, and you're going to start swimming. By the time you get up to the surface, you're dizzy. You feel stuff coming out of your nose, out of your ears. They pull you in. You are hemorrhaging out your nose and your ears, and you're beginning to turn blue. Why? Well, it all goes back to nitrogen. Remember, as you're going down, you're breathing in more and more oxygen into your bloodstream. Little bubbles that won't bother you. They're so itsy bitsy, teeny weeny, they're not going to bother you. Okay? But as the pressure outside begins to decrease, as you are swimming up, those bubbles are going to want to come out of the liquid now. They shouldn't be in your blood. And they're going to want to come out. So they form larger and larger bubbles. The deeper you go, the bigger the bubbles. The more shallow you go, the bigger the bubbles. If you have not given yourself enough time to breathe all that nitrogen back out, then those bubbles will form in your blood vessels. And remember, you've got capillaries near your skin that are as tiny as a hair. Okay? So what happens when a big old bubble tries to make its way through the capillaries? Pop goes the blood vessel, and you start hemorrhaging. So they pull you in. They could throw you back into the shark infested water and tell you go and start all over again. No, by this time it's too late. So they'll probably have to call one of those rescue helicopters. They'll swoop in, they'll put you in the little harness, they bring you back up straight to the hospital. All the hospitals on the coast are going to have these. They're called hyperbaric chambers. They're chambers that you can actually adjust the pressure on. So they rush you in there and they start increasing the pressure. As they increase the pressure, the bubbles start getting tinier and tinier and stop making so much damage. Once they get it back to the original pressure that you were, and they start now doing what you should have done if it hadn't been for that shark. Little by little, they slowly start decreasing the pressure so that you have a chance to breathe it all back out. This is called getting the bends. A scuba diver with the bends is a scuba diver that's in big trouble. People die from this every year. Okay, anybody here a scuba diver? If we were near the coast, I bet some of you would be. So the rule typically is you can't rise any faster than bubbles are rising. So if you have to say goodbye to your bubbles, as there's a big old shark coming after you, you're in big trouble. So how do gases act when they're in that tank? Oh, I never answered the question, why do they use helium? Helium is a teeny, it's just, helium is 2 protons, 2 neutrons. That's how teeny and so tiny. Compared to nitrogen, it is microscopic. Helium is actually so little, it'll go straight through your chest and come out that way. So helium, it's too tiny to form bubbles. So helium will not form the bubbles. That's why you can breathe a combination of 80% helium, 20% oxygen, and you're just fine. Okay? That's why for deep sea divers, they give you helium oxygen. And if you're concerned about talking squeakily, why would you be talking if you're scuba diving? Stop talking. You should not be talking. There's no way you can talk. You need air in order to talk. You're surrounded by water. No one will hear you. Okay? All right. So whether it's helium plus oxygen or nitrogen plus oxygen, the key thing is you just can't have pure oxygen. So they could have replaced it with anything. It was going to act the same. Gases that are in combination act as if they are alone. They ignore each other. They're individual entities. This was first described by our old friend John Dalton. What is Dalton's law? For a mixture of gases, the total pressure exerted is the sum of the partial pressures of the gas present. When we talk about partial pressures, we're talking about the pressure that each individual exerts, as if they were alone. Okay, so let me give you a for instance. If you have half a mole of hydrogen and it's exerting 2.4 atmospheres of pressure, and you have 1.25 moles of helium and it's exerting 6 atmospheres, what happens if you combine them together? 2.4 plus 6 equals, in other words, can you people add? If you can, you're going to be all right with these questions. If you can't, use a calculator. What equation do we use to more succinctly explain Dalton's law? Succinctly, concisely, more precisely, no, not even precisely, more efficiently. P total is equal to pressure of A plus pressure of B plus pressure of C dot dot dot. You know what the dot 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 means? However many you need. I think this is actually in the back of your periodic table. Oh yeah, right there. So 3 dots. Check this out. If you have 1.75 mole of just helium, it will have a pressure of. If you have 3 different gases, but they still equal out 1.75, guess what? Same pressure. Doesn't matter how many gases you have. All that matters is how many gases you have. All right, let's see if we can tackle this question. You have three gases, each in a 3-liter tank. Gas A exerts 5 atmospheres, while gas B exerts only 3 atmospheres, and in gas C, 2.0 atmospheres. If you take all 3 gases and shove them into the same kind of tank, what will be the new pressure? 10. How do you know? Folks, the fact that he can get this right should make everyone feel good about. He's from Connecticut. They don't even know the colors right. Okay? If he can add these 3 numbers, then so can you. It is literally 5 plus 3 plus 2.
That easy. The 3 on your tank doesn't even matter. Where'd you get the whole they don't colors thing?
I'm just assuming they're Yankees. Who knows what they know? They know bagels. That's all they know.
That's all they know. Bagels. I mean, bagels are okay.
What is the most practical gas law? It's called the ideal gas law. Its basic assumption is that gases cannot liquefy or interact in any way. What is the problem with this? Well, they do liquefy and they do interact. But we assume they don't. But they do, Mr. Marino. But assuming they don't, all of this works. But they do. They really do. But let's pretend they don't. And as long as we pretend they don't, we're okay. Under what conditions do ideal gases, I think I talked about this before, in order to get them to interact, what 2 things you have to do to them? Kanan.
Increase pressure.
Shove them close together, which is increase pressure, and get them to want to cuddle. Bunch of kindergartners in a very, very, very cold closet, and you're going to get a liquid. Remember, what is temperature again? Average kinetic energy. Some are hotter, some are colder. Let's see if this video is working.
One of the things that teachers who aren't me tend to say is that you need to learn all this stuff because someday you'll be out there in the real world and you'll need to know how to do all the things that adults do. First of all, I don't really believe this because I think you should be learning just because learning is fun. But I also remember when I was a kid hearing that and thinking that this real world couldn't be that much tougher than high school because it was pretty tough. But looking back, I can tell you that life does indeed get a bit more complicated after 12th grade with jobs and bills and raising kids and taxes, and I haven't done any of the raising kids, but I've seen it and it looks really hard. And then there's always knowing that there's always more work waiting to be done. But the truth is, while it's more complicated, it's not really that much harder than high school. Most adults rarely have to take pop quizzes or final exams or ask permission to go to the bathroom, wear orthodontics, have a curfew, live on an allowance, find a date for prom, or shower in a room full of people that they don't like, all while trying to build your first real lasting relationships. Yes, real life is tough, but the ideal world of teenagers? Not ideal. Turns out that the biggest problem isn't so much that the pressure increases in real life, you just have to learn a few new tricks to deal with it. And the same goes for gases.
All right. No, we don't have time.
Welcome to another edition of Crash Course Today. What is that smell? Oh, thanks for the rotten eggs. Who is this? Why are we doing this? I mean, are we going to be using this to illustrate some kind of scientific principle? Because we probably could have, used, some lilacs or something that wasn't egg. So, We're saying, I can smell it when I'm this close, but if I were farther away, I couldn't smell it. Now, eggs produce hydrogen sulfide when they start to go bad, which smells like sulfur. That's what we think of when we think of the sulfur smell. It takes time for the molecules of hydrogen sulfide to make their way to my nose, because obviously gases don't travel from one place to another instantly. It takes some time, since as we've learned over the past couple of weeks, gases have real-life constraints on how they move here in the non-ideal world. These are the rules that determine, say, how fast a leaking tire goes flat, or why helium balloons don't last forever, and of course, how, where, and when we smell stuff. One key to understanding the behavior of a gas is its velocity, that is, the speed and direction that it moves, and that depends on a few important physical factors. You ready to learn more? Let's do it. The smell is coming from the eggs, isn't it?
And that law is called Graham's law. So basically, assuming gas is ideal, how fast a molecule moves is dependent on its size. Let's use Sierra as an example. Sierra versus, we're going to have a race. Sierra versus Robert. The race will begin over there by Mr. Fowler's room Friday at 3:06. So as soon as the 3:06 bell signaling the beginning of the weekend sounds off, they are to race from Mr. Fowler's room to my room. And whoever gets here first gets a prize. Who's going to win? You would think it's Robert because everyone would want to get away from him. But the fact is, as fast as he goes, people will not be able to get away from him. Whereas Sierra is so petite, she will be able to zig and zag, go between people's legs in this crack, between that and this, and probably make her way to my room without colliding much. While Robert, there is no altering course for Robert. Robert just goes on. All sorts of gas molecules are going to run into Robert, and they will probably suffer the consequences of running into Robert. So you may think, well, Robert will just plow right through. Yes, but every time he plows into somebody, he's going to slow them down, or he's going to slow himself down. Sierra, being so teeny and tiny, is probably going to get away with not colliding that often, which means she'll be faster. Why is it the smaller the gas, faster it will move? It will collide less frequently. Another crash on my crash course. Okay, how hard is this? Once again, if you can add, you can succeed. What is the size going to be dependent on? Their molecular mass. So, first things first, take out your periodic tables. Let's add these up. What is 12 plus 4 times 1? Try 16. How about 12 plus 32? 32 plus 32. 16 times 2. All right. So, who's the smallest? Then, so if you're going ascending, diffusion. Diffusion is how fast they can move, how fast they spread out. Ascending diffusion would mean slower to faster. So who would be the slowest? Next. 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 What is the practical application here? Well, your flatulence is H2S, which is 34, CH4, which is 16, H2O, which is 18. Maybe some CO2, which is 44. So, you let one go, your neighbor is first going to smell what?
I see an 18 there.
CH4, methane. Guess what? You can't smell that. You can't smell it. So you're breathing it in. That gas was in somebody's colon a few seconds ago. You're breathing it in, but you wouldn't be able to tell. Don't worry about it, Kanan. You won't be able to tell. Next up, what's going to reach your next? Oh, water. Can you smell water? No, odorless. Next one. Oh man, who did that? You know what? You've been smelling it for several seconds now. You can't smell water and then finally CO2, you can't smell that either. All right, try this one. Then we're done. This is 32, 28, 38, 17. I know you can add, but we don't have time for you to add on your own, so there you go. What does it mean to be descending? You're going down, so from fastest to, so who is fastest? Who is? That is descending diffusion order. All right, get your homework done.